Good morning. Hope everybody's doing well. We are about 3/4 done with those exams, and as soon as we're done, we'll have them up for you. Dr. Ming has been pretty vocal about not showing you guys what's up until we finalize everything, but I think it's looking pretty good overall. Dr. Ming said his grades were good, so he's more or less done with his grades, and we still have to, I have to finish the rest of ours, but yeah, we're pretty much done, so they're coming along. And yeah, so last time we had our exam, but then I told you to watch a couple videos on Laplace transform and properties of Laplace transform. We're just going to go over Laplace transform just a little bit again today and do an example or two, and then get into inverse Laplace transforms, partial fractions, and solving differential equations. So the Laplace transform is a modification or something you do to a function that modifies it into a new function of a new variable. So basically t is usually time, s, even though we don't see the complex number, it's actually a complex angular frequency. Complex angular frequency. But we're not going to really worry about what the t and the s represent. We're just going to say it's a way to manipulate a function very similar to a derivative manipulates a function or an integral manipulates a function. Yeah. So yeah, this is the definition of a Laplace transform. It's an integral from 0 to infinity f of t e to the negative st dt. So that's the definition of a Laplace transform. There are so many different transforms. This is called Laplace transform. There's Fourier transform, there's Hilbert transform, there's so many different transforms. But we're going to learn Laplace transform because why would we want to learn the Laplace transform? So why? Well, we'll see today that Laplace takes derivatives and turns them into algebraic expressions. So instead of working with derivatives, we basically start working with polynomials. Algebraic, really just polynomial expressions. So a Laplace transform can take a differential equation and turn it into an algebraic equation. So a differential equation will eventually go into the Laplace transform and turn into a polynomial equation. And then we'll invert the transform to get the solution. So that's kind of our thought process of why we want to learn Laplace transform. It takes a differential equation, turns it into a polynomial equation or an algebraic equation, and then we can invert that eventually to get the solution to the differential equation. And it also Laplace handles very complicated non-homogeneous DEs very easily. When we would really struggle to find the solution to very complicated non-homogeneous equations, i.e. the forcing function is very complicated, Laplace transform can handle that very easily. So these are kind of the two reasons we want to learn Laplace transform, because Laplace can take a differential equation, turn it into an algebraic equation, and then also we can handle very complicated forcing functions for our differential equations using Laplace transforms. So that's kind of our motivation for learning about Laplace. And you electrical engineers you're just gonna use Laplace and Fourier all the time. So the sooner you get comfortable with it, the better. Also, you mechanicals are gonna use it in your senior year quite a bit. So just hang in there. Obviously, physics, math, this is gonna be a very natural thing for you to learn as well. So just hang in there. It's gonna be good. I think you guys are gonna like it. So, There we go. Let's look at an example here. Example: find Laplace transform of t cubed. So Laplace transform of t cubed. Well, that would be, so the solution is that the Laplace transform of t cubed will be equal to, by definition, the integral from 0 to infinity t cubed e to the negative st dt. So the definition of Laplace transform says take the integral from 0 to infinity function times e to the negative st dt. And now we've got to do integration by parts 3 times. So integration by parts. Integrate by parts. And you're definitely going to want to use tabular. So make a u column and a dv column. And t cubed 3t squared 6t 60, and e to the negative st negative 1 over s e to the negative st 1 over s squared e to the negative st negative 1 over s cubed e to the negative st 1 over s to the 4 e to the negative st, and then diagonal plus, diagonal minus, diagonal plus, diagonal minus. So this Laplace transform is going to be equal to negative t cubed over s e to the negative st minus 3t squared over s squared e to the negative st minus 6t over s cubed e to the negative st minus 6 over s to the 4 e to the negative st from 0 to infinity. And when I say from 0 to infinity, that really means the limit as t goes to infinity. So we're basically plugging in infinity. So it's like negative infinity cubed over s times e to the negative infinity. Or sorry, e to the infinity. So over e to the infinity minus 3 infinity squared over s squared e to the infinity minus 6 infinity over s cubed e to the infinity minus 6 over s to the 4 e to the infinity plus 0 plus 0 plus 0 plus 6 over s to the 4 after you plug in 0 for all those t's. And I'm putting plus signs because it's minus minus. And now infinity cubed over e to the infinity, well, the exponential is going to win and this thing is going to go to 0. It's going to 0, This is going to go to 0, it's going to go to 0, and this is going to go to 0. So actually the answer is just 6 over s to the 4. And that is the Laplace transform of t cubed. So that's it. So that's our Laplace transform of t cubed. And if you don't like that, it's basically saying something like limit as t goes to infinity of t to the n over e to the t equals 0. And you can show that's true for any n. So exponential beats a polynomial. Exponential wins versus polynomial. So you could prove that with like induction or something like that if you wanted to show that the exponential would win. It's basically like a repeated use of L'Hopital's rule n times. But the exponential is going to win, so it's going to go to 0 every time. So those first 4 terms are 0. All right, so that is our first Laplace transform example. The next example is similar. This example, find Laplace of 1. So find Laplace transform of 1, a constant, basically. What's the Laplace transform of a constant? Solution. Laplace transform of 1 is going to be integral from 0 to infinity 1 times e to the negative st dt, which is going to be negative 1 over s e to the negative st from 0 to infinity, which is going to be negative 1 over s 1 over e to the infinity plus 1 over s 1 over e to the 0, which is just 1 over s. So that's a Laplace transform of a constant. And basically the same thing would hold if you had, sorry, that's Laplace transform of 1. Similarly, we could say similarly Laplace transform of c would be integral of 0 to infinity c times e to the negative st dt, and that would just turn out to be c over s. Because the constant could come out of the integral, and then you would just be doing Laplace of 1. So that is an important one to remember. I'm going to give you a list to remember. And if you watch the videos that I told you to watch, you will already have seen the list more or less. Let's look at another function. So example, find Laplace transform of f of t where f of t is equal to, it's a piecewise function, it's 0 for t less than some number c, and it's 1 for t greater or equal to c. So if you graph this function, you have 0 until you get to c. We'll say c is right here. And then you go up to 1. So that's f of t. And we want to find the Laplace transform of this piecewise function. So solution. This is where Laplace transform is going to be very useful for non-homogeneous equations when we have piecewise homogeneous differential equations. So when we have piecewise differential equations, we're going to have to use Laplace transform. So the solution here is going to be, well, the same definition holds. Laplace of f of t is still integral from 0 to infinity f of t e to the negative st dt. Now, you have to break up the function depending on the bounds. So actually, we go from 0 to c. The function there is 0 times e to the negative st dt. And then from 1 to infinity, the function is 1 e to the negative st dt. So, whoops, that should be a plus sign. So, it's from c to infinity. So from c to infinity, the function is 1. And now we integrate only the second integral. The first integral we know is going to be 0. So the first integral is 0. So then we only worry about the integral from c to infinity, which is going to be negative 1 over s e to the negative st from c to infinity. And now I plug in those bounds, and we get negative 1 over s, 1 over e to the infinity, plus 1 over s e to the negative sc. And we know the first term is 0, so this is just going to be equal to 1 over s e to the negative sc. So any questions so far about Laplace transform? I'll take a second. I need to make a modification to my settings. That left side is being cut off a little bit, so post any questions in the chat. Let me know what's up. I'm going to change the left side if I can. Right. Back in business. How are you doing today, Sam? So this is 7.1. This is 7.1. The definition of Laplace transform. Good to hear, Sam. Good to hear. All right, so let's look at another function here. Find Laplace transform of this function. So find Laplace f of t. No problem. Good to see you guys today, Cortland, Sam, anybody else joining us today. Good to see you. Miss you guys. I hate that we can't interact in person. It's been a struggle for sure, not being able to see you guys. But we're making it. We're going to make it. Hopefully you guys are doing well. Find Laplace transform of this piecewise function. It's going to be a very similar idea. Just break it up depending on the interval. So solution here is going to be Laplace of f of t. And we can kind of see it's already going to be 0 on the first two intervals from minus infinity, or 0, anything less than 0. And then from c to infinity, it's also going to be 0. So this is really just going to be the integral from 0 to c, t, e to the negative st, dt. Because anywhere else, it's going to be 0. So we have to do integration with parts again. I'm going to do a tabular integration, u dv, so t1, 0, e to negative st, negative 1 over s, e to negative st, and 1 over s squared, e to negative st. I assume Philip is not here because normally he's the first one to say something in the chat. You hear, Philip? So our integral becomes, let's see, diagonals. This is going to become negative t over s, e to the negative st, minus 1 over s squared, e to the negative st, from 0 to c. Now we have to keep all the terms because we don't have infinity, we just have constants, 0 and c. So this is going to turn into negative c over s, e to the negative sc, minus 1 over s squared, e to the negative sc, plus 0 over s, e to the negative 0, plus 1 over s squared, e to the 0. So the answer is going to be negative c over s, e to the negative sc, minus 1 over s squared, e to the negative sc, plus 1 over s. That's exactly right, Sam. We wouldn't integrate less than 0 anyway, so you're exactly right. We wouldn't even really need to worry about that. So that's a good point. So our answer is negative c over s minus 1 over s squared plus 1 over s. Let's see, did I miss a square? Yeah, that one should be squared. Right there. Yeah, square right there. You're exactly right, Sam. Very good. Now, there are a bunch of Laplace transforms that you kind of need to know by heart. And I'll list some of those now. So good transforms to know by heart. Kind of like in differentiation and integration, we kind of gave you like, or anti-differentiation, we gave you like a bunch of like need to know antiderivatives, and it was like polynomials and exponentials and sine and cosine, stuff like that. Well, we're going to do the same thing here for Laplace transforms. There are a bunch of Laplace transforms that you kind of just need to know without having to think about it. So Laplace transforms you should know by heart. So good Laplace transforms to know. So good Laplace transforms to know. So I'll say the first one that you need to know is constant. Laplace of 1 or Laplace of a constant is just c over s. So you just need to know that by heart, guaranteed. You also need to know, number 2, that Laplace of t to the n is going to be n factorial over s to the n plus 1 if n is a positive integer. So that's pretty important. It has to be a positive integer. If it's not a positive integer, it's much more complicated. I'll write it out, but you don't need to know it. It's a gamma function of alpha plus 1 over s to the n plus alpha plus 1. Not that I think you really need to know this one. Yeah, I won't write anything down that I don't think you need to know, so I'll skip some. The third one I think you really need to know is Laplace of sine kt. Laplace of sine kt is equal to k over s squared plus k squared. Number 4, Laplace of cosine kt be equal to s over s squared plus k squared. The fifth one you're going to need to know is Laplace of e to the at is 1 over s minus a. And those are kind of the most important ones because almost everything else can be derived, or you can get everything else from one of these, just about. But I'll throw one more or two more up, even though we don't use them a whole lot. It's Laplace of hyperbolic sine kt is k over s squared minus k squared. So k over s squared minus k squared. And then number 7 we'll say is Laplace of hyperbolic cosine, which is going to be s over s squared minus k squared. So very similar to sine and cosine, just a minus sign instead of plus. Pretty much everything else we're going to cover is you can obtain from one of these using a theorem that we talk about later. Let me just throw up one more. It's a good one to know. That way you don't have to derive it. T e to the at is 1 over s minus a squared. So 1 over s minus a squared. I would say these 8, if you know these by heart, then you're pretty good to go. There are some more, but yeah, I would say if you know these 8, really you don't even have to know the hyperbolics, because hyperbolic, if you recall, hyperbolic is just an exponential function. So sine h of kt is really just like e to the kt minus e to negative kt over 2. And hyperbolic cosine is really just e to the kt plus e to the negative kt over 2. So it's really just exponential functions. So if you can take Laplace of exponentials, you can take Laplace of sine, hyperbolic sine and cosine. So that's why I say you don't really need to know hyperbolic sine and cosine. Whenever we get to inverse transforms, we'll pretty much break that up with partial fractions anyway to get back to exponentials, which we could then turn into hyperbolic sine and cosine. But if you know hyperbolic sine and cosine, that's perfectly okay. So those are kind of the Laplace transforms I want you to know by heart. Kind of like whenever we talk about derivatives and integrals or antiderivatives, we know a bunch by heart. Kind of the same thing here. We want to have some Laplace transforms just off the top of our head. We can spit them out very quickly. You're going to need to be able to do Laplace transforms and inverse transforms very, very quickly. So hang in there. One more thing in this section is called the linearity property. So linearity property. The linearity property says that Laplace transform of a constant a times f of t plus some function g of t, so a is only multiplied by f, it says that we can take out the constant and we can break up the Laplace transform. So we can say a times Laplace of f plus Laplace of g. So that's the linearity property of Laplace transform. You can break up over a sum, and you can pull constants out, because Laplace transforms are really just integrals, and integrals you can break up over a sum, and you can pull constants out of integrals. So that is the so-called linearity property for Laplace transform. So pretty much anytime you see use the definition to evaluate the Laplace transform, or to find the Laplace transform, or find Laplace transform using the definition, you're going to do the integral. So just anecdote or a note. So anytime you see the words use the definition, that means do the integral. Like we did for all the examples in this section. So like we did for the examples in this section. So that is going to be on your exam. So this is the last section on the second, or the third exam actually. So the third exam coming up, I think it's not next week. Maybe it is next week. Can't remember. I think it's coming up in May actually, so it may not be next week. Maybe the Tuesday after that. So a week from Tuesday, I think. This is the last section on there. So it'll basically just be to use the definition to find Laplace transform. That's the last section on the next exam. So the next exam is going to go from power series solutions through 7.1, which is now definition of Laplace transform, and using integrals to evaluate Laplace transforms. Any questions before we move on? Because we have got to we've got to go into 7.2 next. I want to make sure we're all good. All right, no questions. Trying to slow down. I remember, I remember people saying that I'm just like blowing through material. So trying to slow down. Try not to go too fast. I want to make sure I answer questions. 7.2 inverse Laplace transforms. So this is basically just going to go the other way. If we have a Laplace transform, what was the original function we took the transform of? So just some notation to start off with is that Laplace of f of t equals capital F of s. So that's the notation we use. We use capital letters to denote Laplace transforms, and the corresponding lowercase letter is the original function. So if we have f of s, if we have capital F of S, what was little f of t? So that's the kind of the question we want to answer in this section, is like go the other way. If we have the function in S, what was the corresponding function in terms of t? So we use the inverse Laplace transform to do that. So inverse Laplace of capital F of S is equal to little f of t. So that's the idea. And we call this thing the inverse Laplace transform. This is the inverse Laplace transform. We're not actually going to define the inverse Laplace transform. We're just going to do it like we did for antiderivatives. So similar to antiderivatives, we're just going to go backwards from our Laplace transforms. So inverse Laplace of 1 over s will be equal to 1. So it'd be the inverse Laplace of 1 over s. Inverse Laplace of 1 over s squared would be Laplace, or would be t, because Laplace of t would be 1 factorial over s plus s to the 1 plus 1. So that is the inverse Laplace of 1 over s squared. So for example, those are how we're going to use that. Now, we're going to have to invert a lot of Laplace transforms, and doing so often requires partial fraction decomposition. So inverting Laplace transforms, just want to make a note, inverting Laplace transforms often requires partial fraction decomposition. So we're going to have to do a little partial fraction review here, and I'll just go over some partial fraction review. So partial fraction review. Now, most of the time we're just going to have like a quadratic or cubic or some kind of polynomial in the denominator. So we're going to look at what happens in those cases. So the first thing that could happen is we could have distinct roots, or distinct factors, R1 not equal to R2. And it'll be distinct real factors. So we might have some function as plus b over s minus r1 times s minus r2. So we have two distinct real roots. The partial fractions will become capital A over s minus r1 plus capital B over s minus r2. And once we have those two factors, or partial fractions, we know how to invert those transforms because those are going to go back to exponentials. So that's why we would want to break this up, is because we could go back to those exponential functions that we mentioned in our list of Laplace transforms we really want to know by heart. So if we know the Laplace transforms by heart, we basically know the inverse transforms by heart as well. So this would go back to constant times e to the r1 t plus constant b times e to the r2 t. So that's how we would break up two distinct real roots in the denominator. On the other hand, let's say we have a repeated root. So the second case is a repeated real root. And that might look something like as plus b over s minus r squared. And the way we break that up into partial fractions is a over s minus r plus capital B over s minus r quantity squared. And both of those we can use our chart that we had on the end of the last section to find the inverse transforms of those two. And then the last one, we can have complex roots. So if we have complex roots, we call them r equals, we'll call it lambda plus or minus mu I. So we have a real part lambda and a complex part mu. The way we want to split this up is basically complete the square in the denominator and write it as as plus b over s minus a lambda quantity squared plus mu squared equals, and then the numerator we want to write it as capital A times s minus lambda plus mu b over s minus lambda squared plus mu squared. And when we see some of the translation theorems coming up in a couple of sections, we'll see why we want to write it this way. But if we have complex roots, this is how we want to write the partial fraction pieces. So to get that complex root, you basically complete the square in the denominator and write it that way, s minus lambda squared plus mu squared. And then the numerator, you want to write it as capital A times s minus lambda plus mu times capital B. And once we do that, then we can take the inverse transform. So that's going to be super useful for us. You don't really want to write it as a times s plus b in the numerator. You'd rather write it as a times s minus lambda. And just the best thing I can say right now is just take my word for it. But in the future, you'll see why. So let's look at just a few examples of finding Laplace transforms. So let's example. Inverse Laplace transforms, I mean. So example, find inverse transform of part A, capital F of s equals 1 over s squared plus 3s plus 2. And the second one, capital F of s equals 9s plus 2 over s squared plus 19. So find the inverse transform of these two functions. Capital S, part A, capital F of s is 1 over s squared plus 3s plus 2. Capital B, or part B, capital F of s is 9s plus 2 over s squared plus 19. Let's find the inverse Laplace transform of both of these. So solution, part A, I think we can factor that denominator. We could say 1 over s plus 1, s plus 2. So that's another way we can write capital F of S. So let's find the partial fractions for 1 over s plus 1 times s plus 2. That would be a over s plus 1 plus b over s plus 2. So find the partial fraction pieces. And probably the easiest way to do this one is to cross multiply, say 1 equals a times s plus 2 plus b times s plus 1. And then pick specific values of s to plug in. So I'll plug in s equals -1. So if you plug in s equals -1, you get 1 equals a times 1 plus b times 0. So you get automatically that a is equal to 1. If you plug in s equals -2, you get 1 equals a times 0 plus b times -1. So that tells you b is -1. So really f of s now is going to be 1 over s plus 1 minus 1 over s plus 2. And that is our partial fraction decomposition for this function. And now we can take the inverse transform of these two. So Laplace inverse of 1 over s plus 1 minus 1 over s plus 2. Well, by linearity property of Laplace, the inverse Laplace is also going to have the same linearity property. So this is going to be Laplace of 1 over s plus 1, or Laplace inverse of 1 over s plus 1 minus Laplace inverse of 1 over s plus 2. Now I just need to know what is Laplace inverse of 1 over s plus 1. Well, recall Laplace of e to the at is equal to 1 over s minus a. So here we must have a is -1. So a equals -1, and here a equals -2. From e to the at. So that's going to give us e to the -t minus e to the -2t. And that is our Laplace inverse for this function part A. So I'll take a minute, pause, see if there are any questions. Okay, second one, part B. All we have to do for the second one is actually just write it as 9s over s squared plus 19 plus 2 over s squared plus 19. Also recall Laplace of sine and cosine. Sine of kt was k over s squared plus k squared, and Laplace of cosine kt was s over s squared plus k squared. So we're going to use those two in the second part here. Well, basically k in this one is square root of 19. So k is square root of 19 for sine and cosine kt. And we don't have square root of 19 in the second one like we need, so we're going to put it there, and then we're going to divide out front by square root of 19. So now we have the k in the numerator for the sine transform. The 2 can come out here. So pull that 2 out. And we basically now have it in the form that we need. We're going to pull the 9 out as well. And this is going to become 9 times Laplace inverse of s over s squared plus 19 plus 2 over square root of 19 Laplace inverse of square root of 19 over s squared plus 19, which becomes 9 cosine square root of 19t plus 2 over square root of 19 sine square root of 19t. And that would be our Laplace inverse for this function. Yes, the struggle is real on the brackets. My right bracket is always lacking. My left bracket sometimes is close. But yes, it is a humbling experience to experience Laplace transforms, because you have to write those brackets everywhere. Now, what to do with all this partial fraction stuff? Well, now we solve differential equations. We know how to invert, we know how to do partial fractions. Now we can get to actually solving differential equations. So, theorem basically tells us how to take Laplace transform of a derivative. So theorem, it says Laplace transform of y prime of t is equal to s times y of s minus initial condition y of 0, where Laplace of y of t is capital Y of s, and Laplace of y double prime equal to s squared y of s minus s y of 0 minus y prime of 0. And you could continue the induction. You could say Laplace of the nth derivative of t would be equal to s to the n y of s minus s y of 0 minus s squared, s to the n minus 1 y of 0 plus, minus s to the n minus 2 y prime of 0 plus plus n minus first derivative of y at 0. Minus. These are all minus signs. So that's how you take Laplace transform of a derivative. And I can show you, hopefully, so proof for y prime of t. So let's take Laplace of y prime of t. Well, that's going to be the integral from 0 to infinity y prime of t e to the negative st dt. And what we're going to do is we're going to use integration by parts, where we're going to let u equal e to the negative st and dv equal to y prime of t dt. And so differentiate, we get du. It's going to be negative s e to negative st. V is just going to be y of t. So this thing is going to be y of t e to the negative st minus, which is going to be minus integral negative s e to the negative st times a y of t dt from 0 to infinity. Here 0 to infinity as well. That's going to be y of infinity times e to the negative infinity minus y of 0 e to the negative 0 minus minus is plus s times the integral y of t e to the negative st dt. So that's going to be negative y of 0 plus s times Laplace of y of t, which we could say is s times y of s minus y of 0. So that kind of shows you the idea for y prime, at least. It's just integration by parts. So that's how you can show these results are true. So the derivative of the Laplace transform of y prime is really just an algebraic expression. So Laplace transform takes derivatives and turns them into polynomials. So Laplace turns derivatives into polynomials. And we'd much rather work with polynomials than we would with derivatives. Well, why does that happen? Well, think about it. I mean, Laplace transform is an integral, so it kind of undoes a derivative if you use integration by parts. So it's a really nice property that we have here for Laplace transforms. We can turn derivatives into algebraic expressions in terms of s. And then all we have to do is solve for capital Y, invert it, and we get little y back. So that's pretty much our solution process. Let's look at an example of solving a differential equation using Laplace transform, if there are no questions. So example. I'll write out the example. If you have any questions, just let me know. We'll pause. Example says use Laplace transform to solve. The IVP. Notice you have to have initial conditions. So you have to solve IVPs with Laplace transform. You can't solve a differential equation with no conditions. Well, I say that. We won't try to do that, at least. Kind of have to have these conditions in place. So the IVP, write it over here, is y double prime minus 3y prime plus 2y equals 0. And initial condition y of 0 is 1, and y prime of 0 is negative 1. So we want to find the solution to this differential equation, or this initial value problem, using Laplace transform. So what we do, solution, the first thing we do is take Laplace transform, take Laplace of both sides of the differential equation. That's the first thing we do when we're solving with Laplace transform. So that means Laplace of y double prime minus 3y prime plus 2y equals Laplace of 0. Laplace of 0 is going to be 0 because when you stick integral when you stick 0 into the integral, you'll get 0. And then the left-hand side becomes Laplace of y double prime minus 3 times Laplace of y prime plus 2 times Laplace of y equals 0. So just using that linearity property again. Now Laplace of y double prime, we know is going to be s squared y of s minus s y of 0 minus y prime of 0, and that's all for Laplace of y double prime, minus 3 times sy of s minus y of 0, and that's for Laplace of y prime, plus 2y of s equals 0. Now we just distribute and collect like terms, plug in our initial conditions, and simplify. So get s squared y of s minus s times 1 minus negative 1 minus 3s y of s plus 3 times 1 plus 2y capital Y of s equals 0. So we've kind of taken care of our first step. We've got the Laplace transform of the entire differential equation. I forgot my square again. The second step is to isolate y capital Y of s. I forgot that square in the first term. So now isolate capital Y of s. So that means I need to take the 3 terms with capital Y of s and collect them on the left. So these 3 terms will help me isolate capital Y of s. So capital Y of s can come out, and I'll get s squared minus 3s plus 2 equals. And now I'll move everything else to the right hand side, so that's s minus 1 minus 3, which becomes s minus 4. And now I can isolate capital Y of s by dividing both sides by s squared minus 3s plus 2. So I've got my capital Y of s, the Laplace of y. I've isolated it. So this is the solution. But it's just the solution in terms of Laplace transform. So this is technically the solution. Technically solution. But we should just say it's the solution in the S domain. It's the Laplace of the solution. So what we need to do is now, step 3, invert the Laplace transform. So we're going to invert y, capital Y of s to get little y of t. Invert capital Y of s to get little y of t. So that's pretty much our solution process right there. Now, to invert this, I'm going to do partial fraction decomposition. Let's see, is this denominator factor s minus 1, s minus 2? Yeah. Bam, just like that. S minus 1, s minus 2. So s minus 4 over s minus 1, s minus 2 equals a over s minus 1 plus b over s minus 2. And you'll do the partial fraction decomposition. So partial fraction decomposition gets you a is equal to -2 and b is equal to 3. So y of s is actually -2 over s minus 1 plus 3 over s minus 2, which tells me then that y of t will be -2 inverse Laplace of 1 over s minus 1 plus 3 times inverse Laplace of 1 over s minus 2. And those are both just exponential functions, which is going to be negative 2 e to the negative, or e to the positive t plus 3 e to the 2t. And that is our solution to the differential equation. Take a break, take a minute. You might say to yourself, Dr. Walters, you're an idiot. That took way too long. And you're right, it did. We already know how to solve this differential equation, this initial value problem, don't we? We know we can just use method of characteristics. I can say m squared minus 3m plus 2, get the y1 and y2, e to the t, e to the 2t, get c1, e to the t plus c2, e to the 2t, solve for c1 and c2, just like that. And you're absolutely right. That is perfectly okay. But in the future, there are going to be some functions, some right-hand sides, some g of t's on the right-hand side that are a little more complicated than 0. So this is a homogeneous equation. You might have a non-homogeneous equation. It gets a little more complicated when you do that. Also, you automatically get the constants of integration, c1 and c2, and you'll also automatically get the particular solution when you use Laplace transforms. So there is a big advantage to using Laplace transforms, especially for non-homogeneous equations. So just hang in there. It's going to be useful. You're going to appreciate it, I think, at some point. So just humor me for now. And try to just absorb. Any questions? Before we do another example, we'll do one more example solving the initial value problem using Laplace transforms. Any questions about this example before we move on? The next one, we have a partial fraction decomposition. I'll try to go a little more in depth into the next one, just to kind of help you review partial fraction decomposition. All right, one more example. Maybe two. So example. It says use Laplace transforms to solve initial value problem. And the initial value problem is going to be y double prime minus 4y equals e to the negative t, y of 0 equals 2, y prime of 0 equals 3. So here we have a non-homogeneous equation. Sure, we could still use method of undetermined coefficients or variation of parameters to solve, but we use Laplace transform and see that it all comes out at the same time rather than doing the homogeneous and non-homogeneous parts separately. So Laplace transform takes care of everything at one time. Now, what do? First step, take Laplace of the differential equation on both sides. So Laplace of y double prime minus 4y equals Laplace of e to the negative t. So take Laplace of both sides. That's going to be Laplace of y double prime minus 4 times Laplace of y equals 1 over s plus 1. All right. If you recall, Laplace of e to the at was equal to 1 over s minus a. And here we have a is negative 1, basically. All right, so now Laplace of y double prime, it's going to be s squared capital Y of s minus s y of 0 minus y prime of 0 minus 4 y of s equals 1 over s plus 1. Plug in our initial conditions. It's going to give us s squared times, well, let's factor out the y of s. Get y of s times s squared minus 4 minus s times 2 minus 3 equals 1 over s plus 1. And that can further simplify to y of s times s squared minus 4 equals 1 over s plus 1 plus 2s plus 3. Well, we actually need a common denominator on the right-hand side before we can add those together. So the common denominator here is going to be s plus 1 over s plus 1. So we're going to have to multiply by s plus 1 to get a common denominator on the right-hand side. And then we can divide by s squared plus 4. So now y of s times s squared minus 4 equals 1 plus 2s plus 3 times s plus 1 all over s plus 1. And so we can isolate y of s completely by saying y of s is going to be 1 plus 2s plus 3 times s plus 1 all over s plus 1 times s squared minus 4. And we probably need to do some algebra in the numerator, and then also factor the denominator to break it up into partial fractions. So one more step to simplify. We could say y of s is equal to, when we do that multiplication and everything, we get 2s squared plus 5s plus 4 all over s plus 1, and factoring s squared minus 4, we can get s plus 2, s minus 2, difference of 2 squares. And now we need partial fraction decomposition. Break that up. Capital A over s plus 1 plus capital B over s plus 2 plus capital C over s minus 2. And this one I'll do a different way. Well, I guess I could plug in specific values. Let me plug in specific values. So the partial fraction decomposition is going to give me 2s squared plus 5s plus 4 equals a times s plus 2 times s minus 2 plus b times s plus 1, s minus 2 plus c times s plus 1, s plus 2. I always struggle with 5s in my Laplace transform problems. They start to look like S's. I try to be very kindergarten-like when I write my 5s. And now I'll plug in specific values for S, and I guess we could say S equals -1 first. So if S equals -1, then we would get 2 minus 5 plus 4 equals A times 1 times -3. And so we could get A is automatically -1/3. So on the left, what we would get -1 plus 2, so that'd be 1, and divide by -3, so A is -1/3. If we plug in S equals 2, we would get 8 plus 10 plus 4 equals A times 0, B times 0, C times 3 times 4. So we'd actually get C is, let's see, 18, 22, 12. Let's see, I screwed that up. 18, 22, 12. S equals 2, 3, 4, 12. Two times 2 squared, 10, 4. Looks right. So C is going to be 22/12. And somebody help me out. Doesn't feel right. Feels like I'm missing something. And then plug in S equals -2. And we'll get 8 minus 10 plus 4 equals, let's see, the first one's 0, the next one is B times -1 times -4. So we get B is equal to, see, 2 over -4. And then a 2/4, which is 1/2. I can actually say that's 11/6. That's like we're good. So -1/3, 11/6, and 1/2. So we can rewrite this as -1/3, 1 over S plus 1, plus 1/2, 1 over S plus 2, plus 11/6, 1 over S minus 2. So that is the Laplace transform of our solution, and now we just need to invert this to get the original function, the original solution, y of t. So the inverse Laplace y of t is going to be Laplace inverse of -1/3, 1 over S plus 1, plus Laplace inverse of 1/2, 1 over S plus 2, plus Laplace inverse 11/6, 1 over S minus 2, which is going to be -1/3 e to the negative t plus 1/2 e to the negative 2t plus 11/6 e to the 2t. And that is our solution to the differential equation, the initial value problem. Notice how we get the constants and we get the particular solution all in one. We don't have any extra work It's pretty nice. So we get the entire solution, the entire unique solution, all at once. So that is our solution. That's our process. Any questions? Again, I'll slow down, answer any questions, take a second. We'll do one more. Got a little time, so we'll do one more example. It's got a different Laplace transform in it whenever we have to go backwards, so I just want to cover it. It's one that I said would be good to know, but not necessarily one that you need to memorize, but we'll just go with the fact that we wrote it down earlier. That way we can find its inverse transform. It's basically when we have the repeated root from our partial fraction decomposition that we'll have this problem here. So let's look at the initial value problem. Use Laplace to solve. Initial value problem. And that'll be y double prime plus 2y prime plus y equals e to the t. Y of 0 is 0, y prime of 0 is -2. So solve the initial value problem with Laplace transforms. Right, so the solution process is the same. We just take Laplace of both sides. Hopefully it's starting to get to be a little natural. So Laplace y double prime plus 2y prime plus y equals Laplace e to the t. And that's going to be s squared y of s minus s y of 0 minus y prime of 0 plus 2 times s y of s minus y of 0 plus capital Y of s equals 1 over s minus 1. Now we simplify, try to isolate capital Y of s. So Y of s on the left we can factor out. It's going to be capital Y of s times s squared plus 2s plus 1. And then the rest we can say, let's see, that's going to be minus 0 plus 2 minus 0 equals 1 over s minus 1. And we can further simplify. We can say y of s equals, well, sorry, keep that factor on the left, y of s times s squared plus 2s plus 1 equals 1 over s minus 1 minus 2. Again, find a common denominator on the right. So multiply top and bottom by s minus 1 over here. Get that common denominator. So we get y of s times s squared plus 2s plus 1 equals 1 minus 2 times s minus 1 all over s minus 1. So then we can say that capital Y of s is equal to, let's see, that's going to be negative 2s plus 3. Negative 2s plus 3 over s minus 1 times s squared plus 2s plus 1. So that's actually negative 2s plus 3 over s minus 1 times s plus 1 squared. And so we need some partial fraction decomposition for this negative 2s plus 3 over s minus 1 times s plus 1 squared. So negative 2s plus 3 over s minus 1 s plus 1 squared. Partial fractions are going to be a over s minus 1 plus b over s plus 1, and then c over s plus 1 squared. So that's going to give negative 2s plus 3 equals a times s plus 1 squared plus b times s squared, well, I should say is s minus 1 s plus 1 plus c times s minus 1. And again, I'll plug in some strategic values to try to eliminate some terms. So if we plug in s equals 1, what do we get? Well, we get 1 on the left, and a we get a times 2 squared. This is 0, this is 0. So a is going to be 1 over 4. And then plug in maybe s equals, let's see, negative 1. S equals negative 1. What do we get? On the left we get 5. On the right we get 0 for a, 0 for b, negative 2 for c, so c times negative 2. So we get c equals negative 5 halves. And you could plug in s equals 0, and then you already know a and c, and you can get b. So you get 3 equals some stuff, and eventually you'll get b is negative 1/4. So your y of s is actually 1 over 4, 1 over s minus 1, minus 1 over 4, 1 over s plus 1, minus 5 over 2, 1 over s plus 1 squared. And now we need to invert that. The first two, those are just exponentials. The third one is actually one that we wrote down in our chart. And it's an exponential times t. So let's look at inverting this. So then y of t is going to equal Laplace inverse of 1 over 4, 1 over s minus 1, plus Laplace inverse of negative 1 over 4, 1 over s plus 1, plus Laplace inverse negative 5 halves, 1 over s plus 1 squared. And that one that I told you, remember, was Laplace of t e to the at is 1 over s minus a squared. So basically we have a is negative 1. So that's going to give us our Laplace transform. So 1 over 4 e to the t minus 1 over 4 e to the negative t minus 5 halves t e to the negative t. And that's our solution. And like I said, everything is taken care of all at one time. We have the constants C1 and C2, and we have our particular solution. Any questions? Next time, we will start looking at shifting theorems and much more interesting functions and solving differential equations with very complicated g of t, so very complicated non-homogeneous equations. Caleb, so I guess there's also the assumption that Laplace always produces linearly independent. Yeah, exactly. So Laplace will give you the solution, and the solution is unique. So yeah, it's exactly going to give you the same thing. It's the same solution as what you would get if you were using method of undetermined coefficients or variation of parameters. So yeah, it automatically gives you everything that you would have gotten using what we did in chapter 4. It's just a different way to get there. Same answers though. Exactly. Great point. Great question. Next time, we'll get into some properties, some more properties of Laplace transforms, shifting theorems, things like that. Much more interesting functions to look at, and they will help us solve much more complicated differential equations. Exactly, that's where that extra t is coming from. Actually, let's think about it. Let's just go back and try to solve that differential equation without Laplace. What would we do? Without Laplace, we would get m squared plus 2m plus 1, which means m plus 1 squared, which means m equals negative 1 is repeated. So that's why we have c1 e to the negative t plus c2 t e to the negative t, and our yp would be a e to the t. So that's what we would have done for chapter 4. So that's why that extra t is there, because it's actually from our repeated root from our characteristic equation. So Laplace takes care of all of this, no problem. You don't even have to think about it for Laplace. You just have to know how to do partial fractions. we also have to know how to invert the Laplace transform, but for the most part, it's much more clean, in my opinion. I think it's a very nice process. And on the exam, we'll give you a Laplace transform table. We'll give you a Laplace transform table. Which is really nice. Again, it's open book, open notes, so you would have had that anyway. But yeah, it's really nice. However, don't forget that you're better off knowing things by heart than you are like looking them up. So this would only be like if you had a really only to get you out of a jam, like we mentioned already. So don't rely on that. Other questions, comments? Beautiful day here. Nice and sunny, blue sky, a few clouds, dark clouds, but mostly sunny, blue sky. Hopefully you guys are doing well. Hopefully you have a good day. You've made it through some of these storms. You've made it through everything we're going through right now. So hopefully you're hanging in there. You're going to make it. It's going to be good. We'll be okay. If nothing else, I'll talk to you guys later. Have a good afternoon. Have a good rest of your day and the rest of your week and weekend. I'll let you know as soon as the grades are in on Moodle. I'll put them in your folders as well. Talk to you guys later.